Hi, everybody. I am Emily Diana. I'm very pleased to be here today and excited to finish off our first session. I'm a rising fifth-year student at the University of Pennsylvania in the Statistics and Data Science Department. And I will be speaking about a paper that is soon to appear, in fact, 2022, Multiaccurate Proxies for Downstream Fairness. And I would like to acknowledge and thank all of my co-authors in the work for today. Wesley Gill, one of my advisors, Michael Kearns, Krishnam Kentapati, Aaron Roth, my other advisor, and then Saeed Sharifi Malbajardi. And this is joint work between the University of Pennsylvania and Amazon AWS. Okay, so we've heard a lot about algorithmic fairness this morning, and we've heard about fairness concerns in policing. We've heard about fairness concerns in recidivism algorithms. There was also some news, actually, ironically, from Amazon, where it was found that some of the automated resume filtering algorithms have learned to discard resumes with certain gendered terms in them. And this isn't because, most likely no one was maliciously sitting there saying, oh, if you see this word, discard the resume. It's just that based on patterns that occurred in the data, this was kind of what was happening in the algorithm to minimize whatever loss function was assigned. So algorithmic fairness as a field has been growing, and it aims to understand how these biases occur, prevent bias in machine learning models. We've seen quite an uptick in algorithmic fairness in the research community. So some early work just documenting these cases. Something that I think is quite interesting, where there's this disconnect between some of the legal guidance that protected attributes should not be used in certain types of decision-making, with mathematical results that show that actually this is better for everybody involved in many cases. We heard in the last presentation about some work on incompatibility results. So some of the current challenges are deciding which definitions to use. Already this morning, we've seen a number of different definitions: equality of opportunity, statistical parity, accuracy parity. How do we decide what actually constitutes a harm? So how does perhaps the numbers that come up in the algorithm, how does that connect to what actually happens in the real world? When and how do we intervene? So do we intervene at the data collection stage? Do we intervene when we're imputing missing values? Are we doing post-processing work? And then how do we balance the trade-offs that occur? And all of these talks this morning have been pretty related, so I'll just mention things that we saw, but we saw some of these Pareto trade-off curves, right? And in many cases, that's something that's just baked into the algorithm that it's very difficult to avoid. So the context and the question that I'll be talking about today has to do with situations in which a sensitive feature is not available to the algorithm designer. So often we would like to train a model that is fair with respect to some sensitive attribute, but we're not allowed to see that attribute. And this is a little bit different than the previous talk because it's not just that certain values are missing. We're imagining that you're handed a data set where just that column isn't there. And this could be for legal reasons, like I mentioned before, when perhaps we aren't allowed to use that attribute in making decisions. It could be for policy reasons. So a company may just not want to ask its consumers certain questions because it doesn't want them to feel uncomfortable. So this puts us in kind of a tricky spot because now if we want to create a resume filtering model that is not biased against women, but we can't actually see someone's gender, what do we do? So in the 15 or so minutes that I have, I'll go through the framework for our problem, some of the main results, key insights, experiments, and takeaways. So here's our mathematical framework. We're considering a pretty standard framework. We have a data domain that is a product of non-sensitive features X, a label Y, and sensitive features Z. These are divided into K groups. And I'll just say that for the purpose of this talk, I'm kind of taking the simpler context. You can see the paper for more, more complicated things. So we have these different groups. We have these tuples. We'll imagine that we're going to want to learn some proxy function. This proxy function will come from a class, so we'll call this class G. It maps non-sensitive features to a real valued vector, where every element of this vector gives some information about membership in the corresponding group. So are you in group 1? Are you in group 2? But it's not binary. It gives some like strength of membership. And then there will be a downstream model class that the downstream learner is using. So this could be the CV filtering algorithm. So the way that we are kind of trying to get around this issue of having data that's completely redacted is to think of this learning process in 2 stages. So having a proxy learner, we can imagine that this is a group that has access to some proprietary data. And from this kind of smaller data set, they are able to produce a function that then they can release to the public. And now anyone can use this function to stand in for the true sensitive attribute. So visually, this is what's going on. We have the proxy learner who does get to see Z, so race, gender, whatever the attribute is, as well as the non-sensitive features. The proxy learner will produce this function that creates the proxy. And then the downstream learner, so some company can now take that proxy, take the non-sensitive attributes and the labels, and then use that to train their model. And we wanted to come up with a way to construct a proxy so that they can actually have some guarantees that if this model they train H looks fair with respect to the proxy, that it's also fair with respect to the true attribute. So I alluded to this already. One of the key insights here is that the proxy can and should be real valued. So intuitively, it often makes sense to have the proxy be binary. You're saying, well, if we want to estimate something that's binary, then let's use a binary replacement. Or maybe we want it to be between 0 and 1. But we found that we were able to get the most information if we allow this proxy to be real valued. And we in particular bounded it between 0 and some upper bound M. That's a parameter to be able. So an advantage of having the proxy be, well, in order to use a real valued proxy, we needed to think about how we were formulating these fairness constraints. So this is just one example of a fairness constraint. As I mentioned, there are many different types, definitions of group fairness, and this is just looking at the probability that a model makes a mistake given that a sample is in a certain group. So you notice that this attribute Z sub K is binary. Either the sample is in group K or it's not. And we want to be able to represent this type of fairness constraint with a real valued attribute. So we can rewrite this conditional probability as a ratio of expectations. And it's the expected value of Z and the indicator that there's a mistake on that point over the expected value of Z. Now, what's nice here is that this doesn't have to be binary, so you can plug in a real valued replacement. So if that first equation holds, if this ratio of expectations with the true attribute Z matches that for the proxy, then if a model is fair with respect to the proxy, that's an example of what it may look like to be fair, then it also satisfies fairness constraints with respect to the true attribute Z. So this is kind of a plug-in principle that is enabled by having the proxy be real valued. So from this principle, we can then formally define a proxy. So we say that Z hat is an alpha proxy for Z if for all classifiers H in our model class, big H, in all groups, if the difference between these two ratios of expected values is very small. And I'll give some more intuition for what these mean shortly. So once we have this definition, we can use it to formulate a linear program and then use strong duality to find an approximate solution. Now, the nice thing here is that once we put this into a linear program, we can see a little bit more what the constraints are doing. So we already saw some examples of linear programs in our second talk. we're minimizing some objective. That objective is actually optional in this algorithm, and that is because what we really need to do is satisfy the constraints. The objective, we put in an MSE objective because intuitively we thought it would help get the proxy close to the true value, but that's optional. So now these two constraints, the first one is saying, okay, I want the average value of Z to be about the same as the average value of Z hat on the whole data set. The second constraint is saying, okay, so we're going to look at all of the models H in our big class H. Now you may say, oh, well, what if H is infinite? So we can use Sauer's lemma. We can create kind of a discrete set that sufficiently approximates the model class. For every one of those models, we want on the point to which it makes a mistake, we want the average value of the proxy and the true attribute to be the same. If we can satisfy those two things, then we can satisfy this desired equality. And these constraints are multi-accuracy constraints. So it's a slightly weaker version of multi-calibration that we saw in the first talk. And for the statisticians in the room, what it's saying is that we want Z hat to be an unbiased estimator for Z on the set of points where H errs. So we want the expected value of Z hat to be Z on those points. So this is an overview for how the proof works to show that we can actually come up with an approximate solution to this linear program. And Georgie talked a little bit about this. So we can rewrite our linear program using strong duality as a Lagrangian. We're going to treat this Lagrangian as some utility function in a zero-sum two-player game. One player wants to minimize it, one player wants to maximize it. The primal player will be minimizing, the primal player controls the proxy. The dual player wants to maximize it, they'll control these constraints. They'll control the lambdas. What the lambdas are doing here is they're saying, oh, I found a model where Z and Z had are really different on the error points. So I'm going to upweight that model so that unless you fix that, this Lagrangian value is going to be huge. So under appropriate conditions, this needs to be convex concave in the primal dual variables. And we also need the spaces for the variables to be convex compact. Then the min-max value, or minimizing over Z hat after maximizing over lambda is equivalent to maximizing over lambda after minimizing over Z hat. And we use this to create a two-player game and spit out an approximate solution. So there are a couple different settings for this. I'm just going to go over the simpler setting again. So in this setting, we want our two players jointly to have low regret. So in hindsight, we want it to be the case that they could have done much better than they did in real time. So the proxy learner who controls the proxy is going to use online gradient descent. The auditor uses a best response with a cost-sensitive classification oracle. This cost-sensitive classification oracle is a heuristic in practice. This is one of the areas where it is kind of hard to make the practice match the theory. And Freud and Shapiri show that if a sequence of actions for the two players jointly has low regret, then the uniform distribution over each player's actions form an approximate equilibrium. Okay. So with that, you can imagine that we have implemented this two-player game. We've come up with this kind of randomized strategy that satisfies this theorem. So now we want to see, okay, how does this proxy function actually do? So we simulated a downstream learner and trained a model to be fair with respect to 4 representations of the sensitive feature. So we looked at what happens if we train this downstream model H to be fair with respect to Z, the true attribute. What if we use a standard baseline proxy, so something like a logistic regression? This is something that people might just commonly use in the literature. And then we took two variants of our algorithm. So the H proxy, you can think of it as the purest form of this algorithm. So your only goal is to satisfy the constraint. Your only goal is to find a proxy that is multi-accurate. The MSE proxy has that additional mean squared error objective. This is mostly for our curiosity. And we conducted experiments on the ACS dataset. It's a superset of the adult dataset. And we looked at a bunch of different varieties, but the plots I'll show today are from the income dataset. It has the same prediction task as adult. We're looking to see whether people's income is over 50,000. So here is an example. Here are our first example. This is on the ACS income data set with race as a sensitive feature. So I think contrary to the previous talk, the models in the lower left are the best. So the y-axis is error disparity. The x-axis is error. So we want everything to be close to the origin. So as you would expect, if we train a model to be fair with respect to the true labels, then we get kind of a dominant Pareto frontier. Next best is the H proxy. After that, the mean squared error proxy. And both of those do quite a bit better than had we just estimated race with a logistic regression. This next one is has much less of a trade-off. I think partly age just ends up being kind of a less expressive feature when we're trying to optimize for fairness. But what's interesting here is that you see that the baseline proxy does a little bit better, or it does a little bit worse than our like pure H proxy, but a bit better than the one with the added objective. So the intuition there is that the objective could actually be distracting a bit from your goal. And here's a similar result with a little bit more disparity. And these are all positive results because, and there haven't been many positive results actually in this area. So this is exciting. So we're seeing that the H proxy you lose just a little bit of fairness trade-off compared to the true attribute, but not much. So we showed that it is possible to find these proxies efficiently. They kind of will achieve similar trade-offs. Now, as I mentioned, there are heuristics that you have to use. So not all plots are going to have this kind of expected ordering. And then these results also depend on the assumption that the proxy learner and the downstream learner are using data from the same distribution, which we know that in practice isn't going to hold. So this is an interesting kind of future area of understanding what happens if that assumption fails and how we can address that. And thank you.